Hello everyone, today I'll give you an introduction to proofs. First of all, let me show you some basic concept. This symbol n represents a set of all natural numbers. This symbol n represents a set of all natural numbers. Natural numbers are numbers 1, 2, 3, 4, 5, and so on. In some book, they may include 0, but it doesn't matter. It's the same thing. Natural number is a set of numbers 1, 2, 3, 4, 5, and so on. You may want to include 0, but it doesn't matter. G with a double slash in the middle. G represents a set of all integers. G represents a set of all integers. Integer could be either positive or negative whole numbers. So we have 0 in the middle, 1, 2, 3, 4, and so on. Could be -1, -2, -3, and so on. Integer including positive and negative whole numbers. And we have two types of integers. Could be either even number or odd number. We have two types of integers. Could be even or odd. Integer could be either even or odd. There are two types of integers. It could be either even or odd. How do we define even and odd numbers? If s is equal to 2 times n, where n is an integer, then we say x is even. If s is equal to 2 times a whole number, then s is even. How do we define odd number? If s is equal to 2m plus 1, where n is an integer, then s is odd. If s is equal to 2m plus 1, where n is an integer, then s is odd. There are two types of integers. Could be either even or odd. If s is even, s is equal to 2n, where n is an integer. If s is odd, then s is equal to 2m plus 1, where n is an integer. Next, let me introduce rational numbers. Q represents rational numbers. How to define rational number? If s is equal to a over b, where a and b are integers, and b is not 0, then s is a rational number. Then we say s is rational. If s is equal to a over b, where both a and b are integers, with b not equal to 0, then s is rational. Which means if s is equal to a whole number over a whole number, then s is a rational number. If s is equal to whole number over whole number, then s is rational number. Those are some basic concepts. Now, based on this, let's do some simple proof first. First example, show that if s is odd, then 4x plus 9 is even. Show that if s is odd, then 4x plus 9 is even. So start from assumption, start from the hypothesis, try to prove the conclusion. Start from the hypothesis, start from here, try to prove the conclusion. That's what's given, that's what we want to prove. So start from what's given. Prove from the conclusion. Start from what's given here. If s is odd, we try to prove that 5s plus 9 is even. Let's prove it here. Since s is odd, then s equal to 2m plus 1 by definition of odd number. Since s is odd, s equal to 2m plus 1, where n is an integer. Then we try to show this number 5s plus 9 is even. 5s plus 9 here can be written as 5 times 2s plus 1 plus 9. I can replace this x with 2m plus 1. Then if I simplify, I can distribute 5. I get 10m plus 5 plus 9. That's 10m plus 14. I try to show this number is even. Means I try to write this number in the form of 2 times the whole number. In the form of 2 times the integer. So we try to write it in the form of 2 times the integer. Here I can try to factor. I can factor power out 2. If I power out 2, I get 7n. So I got 5n plus 7. If I power out 2, I get 5n plus 7. And we know that since n is an integer, 5 times integer plus number 7 is an integer. So no, this part is an integer. Since 5x plus 9 equal to 2 times 5m plus 7, where 5m plus 7 is an integer, then 5x plus 9 is even. Since 5x plus 9 equal to 2 times the integer, that's in the form 2 times the integer, then 5x plus 9 is even. Next example. Show that if s is even, then 3x plus 5 is odd. Show that if s is even, then 3x plus 4 is odd. So start from what's given, try to prove what we want here. Start from what's given, try to prove what we want. So start from s is even, try to prove that 3x plus 4 is odd. So prove it. Since s is even, then by the definition of even number, s equal to 2n, where n is an integer. Since s is even, then s equal to 2n, where n is an integer. Then we try to prove this number 3x plus 5 is odd. Three x plus 5 equal to 3 times plugging 2n for x plus 5. If I simplify, I get 6n plus 5. The goal is to prove this number 3x plus 5 is odd. And we know that odd number is defined as s equal to 2m plus 1, where n is an integer. Odd number is defined as s equal to 2m plus 1, where s is an integer. So we try to prove this number is odd. That means I try to put this number in the form of 2m plus 1. So in order to do that, I can rewrite 5 first. So number 5 can be written as 4 plus 1, because I try to write this number in this form. So I write 5 as 4 plus 1. Then for the first two numbers, I can factor power out 2. For the first two terms, I can factor power out 2. If I power out 2, I get 3n plus 2 plus 1. Since n is an integer, then 3n plus 2 is also integer. 3n plus 2 is also integer. So since 3n plus 5 equal to 2 times the integer plus 1, then 3n plus 5 must be an odd number. Since 3n plus 5 equal to 2 times the integer plus 1, it matches this form, then 3s plus 5 is odd. Next. Show that the product of two odd numbers is odd. Show that the product of two odd numbers is odd. So we try to prove that the product of two odd numbers is odd. So we can start from the two odd numbers here. Start from the two odd numbers here. We try to show their product is odd. So let x and y be two odd numbers. Let x and y be two odd numbers. Start from what's given here. Try to prove that their product is also odd. Let x and y be two odd numbers. Then x equal to 2n plus 1. And for y, don't write 2n plus 1, write 2k plus 1. Don't use the same letter twice, because x and y, they are different numbers. They are not the same number. So use different letters. S equal to 2n plus 1. Y equal to 2k plus 1. Don't use n here, because x and y, they are different numbers. So s equal to 2n plus 1. Y equal to 2k plus 1. Where both n and k are integers. So if s and y are odd numbers, then s equal to 2 times the integer plus 1. Y equal to 2 times the different integer plus 1. That's how we set up the problem. S and y are odd, then s equal to 2n plus 1, y equal to 2k plus 1, where n and k are integers. Next, we try to show that their product is odd. Product means x times y. Product of two numbers means x times y. Product means multiplication. X times y, x is 2n plus 1. Y is 2k plus 1. S is 2n plus 1. Y is 2k plus 1. When we multiply, we need to distribute. Distribute, we get 4nk plus 2n plus 2k plus 1. We try to put it in the form of 2n plus 1. We try to write this number in the form of 2 times some integer plus 1. So for the first three terms, I can factor 2 out. If I factor 2 out, I get 2nk plus n plus k plus 1. If I factor 2 out, I get 2nk plus n plus k plus 1. Since both n and k are integers, 2 times n and k is integer. Integer plus n and k is also integers. Since all these numbers are integer, we get another integer here. Since x times y equal to 2 times the integer plus 1, then x times y must be a number. Which means the product of two odd numbers is odd. Next example. Show that the sum of two rational numbers is rational. Show that the sum of two rational numbers is rational. So let's prove it. We start from two rational numbers. We try to prove that their sum is rational. Start from two rational numbers. We try to prove that their sum is rational. So start from two rational numbers. Try to prove that their sum is rational. Let x and y be two rational numbers. We try to show that their sum is also rational. How do we define rational number? Rational number is in the form of a over b, where a, b are integers and b is not zero. That's how we define rational number. Rational number is always in the form of a over b, where a, b are integers and b is not zero. So since x and y, they are rational numbers, I can say then x is equal to a over b, y equal to, use different letters. Since x and y are different numbers, use different letters. Y equal to c over d, where a, b, c, d are integers, and the denominator b and d cannot be zero. A, b, c, d are integers, and the denominator b and d cannot be zero. So that's x and y. Next, we try to show that their sum is rational. Sum means addition. Sum means addition. So we have x plus y. X plus y equal to a over b plus c over d. When we add two fractions, we need to find common denominator first. Find common denominator first. Here, common denominator is b times d. Here, common denominator is b times d. Common denominator is b times d. For the first fraction, I multiply top and bottom by d. I multiply top and bottom by d. I get a d. For the second fraction, I multiply top and bottom by b. So I get bc. Then here we see that since a, b, c, d are integers, integer times integer is integer. Integer times integer is integer. And integer plus integer is integer. The numerator is integer. The denominator, b times d, integer times integer is also integer. And also, since b is not zero, and d is not zero, then their product cannot be zero. And b times d cannot be zero. Since b is not zero, d is not zero, their product cannot be zero. So next, since s plus y equal to ad plus bc over bd, where the numerator ad plus bc is an integer. The numerator ad plus bc is an integer. The denominator bd is an integer. And the denominator bd is not zero. Since the numerator is an integer, the denominator is an integer, and the denominator is not zero. Since the numerator is integer, denominator is integer, and denominator is not zero. then this number is a rational number. Then x plus y is a rational number. Next, show that the reciprocal of a non-zero rational number show that the reciprocal of a non-zero rational number is also rational. Show that the reciprocal of a non-zero rational number is rational. So we start from a non-zero rational number. We try to prove its reciprocal is also rational. Start from a non-zero rational number. Try to prove its reciprocal is also rational. So let x be a non-zero rational number. So let x be a rational number. Let x be a non-zero rational number. Then s equal to a over b. Then s equal to a over b, where a, b are integers and b is not zero. Since x is a non-zero rational number, we can also say that also s is not zero. S equal to a over b, where a and b are integers and b is not zero. Also, since s is non-zero rational number, s is not zero. That's what's given. Next, we try to prove that its reciprocal is rational. We try to prove its reciprocal is rational. Reciprocal means 1 over x. Let's call it reciprocal. 1 over x equal to 1 over a over b. 1 over x equal to 1 over a over b. That can be rewritten as b over a. We know that a and b, they are both integers. In order to show this is a rational number, we need to show that top and the bottom, they are both integers. And also, we need to show that the bottom cannot be zero. Here, how do we know the bottom is not zero? How do we know the bottom is not zero here? How do we know a is not zero? Based on what's given, how can we prove a is not zero? Based on what's given, how can we prove a is not zero? Since s is equal to a over b, let's try to prove a is not zero. Since s is equal to a over b, then a equal to x times b. Since s equal to a over b, then a equal to x times b. Since s is not zero, and b is not zero. Since s is not zero, b is not zero, then a cannot be zero. Since s is not zero, b is not zero, then a cannot be zero. So 1 over x is integer over integer, and the bottom is not zero, then 1 over x is rational. Since 1 over x equal to b over a. Where the top and the bottom are integers. Where the top and the bottom are integers. And the bottom is not 0. Then 1 over x is rational. Since 1 over x equal to b over a, where the bottom a is not 0, then 1 over x is rational. That proves that the reciprocal of a non-zero rational number is rational. Let's complete the proof. 1 over x is called the reciprocal of x. So the reciprocal of x is rational. Let's complete the proof. Next, show that if 7x plus 6 is even, then x is even. In general, we try to use what's given here to prove what we want. What's given here is 7x plus 6 is even. We want to prove x is even. If we try to prove it directly, it may be too hard. It's too hard to use this given information to prove what we want. It's too hard to use this given information. So if it's too hard to prove it directly, let's try indirect proof. Let's try indirect proof. One of the indirect proof is called proof by contraposition. One of the indirect proof is called proof by contraposition. One of the indirect proof is called proof by contraposition. In general, we try to prove P implies Q. If P, then Q. Remember, this statement is equivalent to not Q implies not P. That's a contraposition. That's the contrapositive of this statement. Not Q implies not P is the contrapositive of this statement. And we know that they are logically equivalent. P implies Q is logically equivalent to not Q implies not P. These two statements, they are logically equivalent. So if direct proof from P to Q is too hard, we try to use indirect proof. We try to prove that not Q implies not P. We try to use indirect proof that not Q implies not P. So this statement is P. This statement is Q. If P, then Q. Now we'll try indirect proof. Assume not Q. Proof for not P. Let's call indirect proof. Assume not Q. Try to prove for not P. So proof by contraposition. Proof by contraposition. Proof by contraposition. Assume not Q. Proof for not P. So here we assume x is not even, means x is odd. Assume not Q. Assume x is not even. That means x is odd. Assume x is odd. Try to prove not P. Not P means 7x plus 6 is not even, which means 7x plus 6 is odd. We try to prove 7x plus 6 is odd. Assume x is odd. We try to prove 7x plus 6 is odd. Assume x is odd. Then s is equal to 2n plus 1, where n is an integer. Assume s is odd. Then s is equal to 2n plus 1, where n is an integer. Then 7x plus 6 equal to 7 times 2n plus 1 plus 6. Replace x with 2n plus 1. Then distribute 7, we get 14n plus 7 plus 6. Distribute 7, I get 14n plus 7 plus 6. That can be rewrite as 14n plus 13. I try to prove this number is odd. I try to prove 7x plus 6 is not even, which means 7x plus 6 is odd. In order to be an odd number, I try to write this number in the form of 2 times some integer plus 1. I try to write this in the form of 2 times the integer plus 1. So let me rewrite 13. 13 can be rewritten as 12 plus 1. Then for 14n plus 12, I can factor 2 out. If I factor 2 out, I get 7n plus 6 plus 1. 2 times 7n plus 6 plus 1. Since n is an integer, 7 times n plus 6 must be an integer. Since n is an integer, 7 times the integer is an integer. Integer plus integer is integer. So 7x plus 6 equal to 2 times the integer plus 1. Then it must be odd. So 7x plus 6 is odd. That's not P. So start from not Q, I prove not P. That's called proof by contradiction. That's an indirect proof. Instead of proof P implies Q, P implies Q is called direct proof. This way, not Q implies not P. That's called proof by contradiction. That's an indirect proof. This way is called direct proof. Not Q implies not P is called proof by contradiction. That's an indirect proof. Next example. Show that if s squared is even, then s is even. Show that if s squared is even, then s is even. Show that if s squared is even, then s is even. If we try to use the given information to prove what we want, it looks too hard to use. It looks too hard to use this information to prove s is even. If what's given is too hard, we try indirect proof. Let's try to prove by contradiction. Assume this is statement P, this is statement Q. We try to use not Q. We try to prove that not Q implies not P. Assume not Q. Try to prove not P. Assume the opposite of the conclusion. Assume the opposite, S is odd. Assume S is odd. Then S is equal to 2n plus 1, where n is an integer. Then I can plug in n. I can plug in x here to show s squared is not even. I can try to plug in x here to show that s squared is not even. S squared equal to 2n plus 1 squared. If I expand a perfect square here, 2n plus 1 squared can be rewritten as 4n squared plus 4n plus 1. S squared can be rewritten as 2n squared plus 2n plus 1 squared, which is 4n squared plus 4n plus 1. I try to show this number is odd, so I try to put it in the form of 2 times the integer plus 1. So for the first two terms, I can factor 2 out. I get 2n squared plus 2n plus 1. Since n is an integer, 2 times n squared is integer. 2 times n is also integer. So integer plus integer is integer. Since n is an integer, this must be an integer. So s squared equal to 2 times the integer plus 1. S squared must be odd. So we assume this is statement Q, this is statement P. We assume not Q, and we proved not P. Assume not Q, prove not P. That's called proof by contradiction. Let's complete the indirect proof here. Next example, show that if sy is even, then either s is even or y is even. Here, what's given is that sy is even. We try to prove that either s is even or y is even. Here, what's given is sy is even. If it's too hard to use, if what's given is too hard to use, we try to prove by contraposition. So prove by contraposition. This is P. This is Q. We try to assume not Q and prove not P. Prove by contraposition. Assume not Q. Prove not P. But by the way, how do we write not Q here? Q here has two parts. Either something or something else. So Q here is in the form of A or B. Here Q is in the form of A or B. How do we find not Q? Not Q is not A or B. If we use De Morgan's law, it's not A and not B. So when we use De Morgan's law, O in the middle become N. So prove by contraposition. Assume not Q, prove not P. So we assume S is not even and Y is not even. That means S is odd and Y is odd. Assume not Q. We try to prove for not P. That means we try to prove that X times Y is not even, which means S times Y is odd. We try to prove that X times Y is odd. Now assume S is odd, Y is odd. Then odd number S can be written as 2m plus 1. And another odd number Y can be written as 2k plus 1. We must use different letters because S and Y they are not the same number. If I use 2m plus 1 here, S and Y will be the same. So we must use different letters for different numbers. Here, both n and k must be integers. Then we try to show that x times y is odd. We try to show that s times y is odd. S times y is 2n plus 1 times 2k plus 1. If we multiply this out, we get 4nk plus 2n plus 2k plus 1. Now, for the first three terms, if I factor 2 out, I get 2 times 2nk plus n plus k. Since both n and k are integers, this part, 2nk plus n plus k, it must also be an integer. Since both n and k are integers, 2 times integer, that's an integer. Integer plus integer plus integer must be integers. So since sy is in the form of 2 times the integer plus 1, it must be odd. So sy, it must be odd. Here we proved not p. Since we use not q to prove not p, let's prove by contraposition. Next example, show that if s is irrational, then x plus 1 is also irrational. What's given is too hard to use. It's not easy to use that s is irrational to prove that s plus 1 is irrational. It's too hard to use what's given. If it's too hard to use what's given, we can try to prove by contraposition. Let's call this P, call this Q. We try to use not Q to prove not P. Prove by contraposition. Prove by contraposition. Assume not Q. We try to prove for not P. So assume not Q. Not Q says S plus 1 is rational. Q says S plus 1 is irrational, so the opposite is S plus 1 is rational. Assume S plus 1 is rational. We try to prove X is rational. Assume S plus 1 is rational. Then, since S plus 1 is rational, that equal to A over B, where A and B are integers, and the denominator B is not 0. If S plus 1 is rational, then S plus 1 equal to A over B, where A and B are integers, and denominator B is not 0. We try to prove that X is rational. So start from this equation, try to show X is rational. S plus 1 equal to A over B. If I try to solve this equation for X, S equal to A over B plus 1. So minus 1. If I solve this equation for X, S equal to A over B minus 1. That can be rewrite as A over B minus B over B. I can write number 1 as B over B. That's A minus B over B. Since A and B are integers, integer minus integer is an integer. And also B by itself is an integer. Since S equal to A minus B over B, where A minus B is an integer, B is an integer, and B is not 0. Since S equal to A minus B over B, where the top is integer, the bottom is integer, and the bottom is not 0, then S is rational. That's not P. Here we proved not P. If we assume not Q and proof for not P, that's called proof by contradiction. Next example, show that the sum of a rational number and an irrational number is irrational. If we try to prove something is irrational, that's very hard. If we try to prove something is irrational directly, that's very hard. So let's try to use indirect proof. However, this statement is not in the form of P implies Q. This statement is not in the form of P implies Q. So we cannot use proof by contradiction because it's not in this form. We cannot find the contradiction. Then next, let me show you a different indirect proof. Let me show you a different indirect proof called proof by contradiction. Another indirect proof called proof by contradiction. That's another indirect proof. Proof by contradiction. What does it mean, proof by contradiction? We assume the opposite of the statement. Assume the opposite of the statement. If we can show that it leads to a contradiction. Contradiction means something impossible. Contradiction means something impossible. If we can show that it leads to a contradiction, which means something impossible, then the statement itself must be true. That's called proof by contradiction. Assume the opposite of the statement. Assume the opposite of the statement. If we can show that this opposite of the statement it leads to a contradiction, which means something impossible, then the statement itself must be true. That means our assumption was wrong. The statement itself must be true. So let me show you here. Proof by contradiction. So we start from what's given here is a rational number and an irrational number. The x be rational and let y be irrational. That's what's given. Let x be rational and let y be an irrational number. We assume the opposite of a statement. This statement says their sum is irrational. We assume the opposite of the statement. Assume s plus y. Assume the sum is rational. Let s be rational, y be irrational. The statement says the sum must be irrational. We assume the opposite. We assume the opposite of the statement. We assume the sum is rational. We try to show that this assumption here will lead to a contradiction. If I can show that this cause something impossible, then the assumption must be wrong. That means s plus y must be irrational. So assume the opposite of the statement. Since s is rational, then s equal to a over b, where a, b are integers and b is not zero. Since s plus y is also rational, then s plus y equal to another rational number is c over d, because that's a rational number. Rational number is always integer over integer, where c and d are integers, and the denominator d is not zero. Then we try to prove something impossible. We try to show something impossible. We have s plus y equal to c over d. If I plug in a here, I have a over b plus y equal to c over d. We have s plus y equal to c over d, s equal to a over b. If I plug in a here, I get a over b. If I plug in a over b here, I get a over b plus y equal to c over d. That means y equal to c over d minus a over b. When we subtract two fractions, we try to find common denominator first. Here, common denominator is bd. For the first fraction, I can multiply top and bottom by b. I get bc minus, For the second fraction, I multiply top and the bottom by d. I get bc minus ad. So we know that since a, b, c, d, they are integers, then the numerator bc minus ad must be integers. Since b and d, they are also integers, so b times d is also integer. And since b is not 0, d is not 0, then since b is not 0 and d is not 0, then their product b times d is not 0. Since b is not 0, d is not 0, their product b times d is not 0. So since y equal to bc minus ad over bd, where the numerator bc minus ad is integer, the denominator bd is an integer, and the denominator bd is not 0, then I can say y is rational. Since the numerator is an integer, the denominator is an integer, and the denominator is not 0, then y is rational. But we assume y is irrational. That's something impossible here. That's something impossible. That's called a contradiction. That's called a contradiction. That's a wrong statement. That's called a contradiction. It's a contradiction. Once we find contradiction, that means our assumption was wrong. Once we find contradiction, that means the assumption was wrong. So x plus y must be irrational. If we find contradiction, that means our assumption was wrong. So x plus y must be irrational. That's wrong. If that's wrong, then x plus y must be irrational. That completes the proof. The sum of a rational number and an irrational number is irrational. That completes the proof. This proof is called proof by contradiction. Proof by contradiction. Another example. Show that square root of 2 is irrational. Show that square root of 2 is irrational. What can we do here? If we try to prove that directly, it's too hard. And it's not in the form of P, it's not in the form of if P then Q. It's not in this form. We can't prove this by contraposition. So another choice is proof by contradiction. Proof by contradiction. We try to assume square root of 2 is rational. We try to show that it will cause something impossible. So proof by contradiction. Assume square root of 2 is rational. We try to prove that it will cause something impossible. So, proof by contradiction. Assume square root of 2 is rational. Then a rational number can be written as a over b. A rational number can be written as a over b. Now a over b is a fraction. For fraction with whole numbers, I can always reduce it to the lowest term. For fraction with whole numbers, we can always reduce it to the lowest term. For example, if I get 10 over 25, I can reduce it to the lowest term, 2 over 5. For any fraction with whole numbers, I can always reduce it to the lowest term. For example, 20 over 18, I can reduce it to the lowest term. For any fraction, if it's not in the lowest term, I can always reduce it to the lowest term. That's called the lowest term. For any fraction, we can always reduce it to the lowest term. So here, I let square root of 2 equal to a over b in the lowest term. I can reduce the fraction to the lowest term. I can always reduce a fraction to the lowest term. A fraction in the lowest term means the greatest common divisor of the top and the bottom is 1. A fraction in the lowest term means the greatest common divisor of top and the bottom is 1. That's called lowest term. The greatest common divisor of the top and the bottom is 1. That's called fraction in the lowest term. So square root of 2 equal integer over integer. For integer, I can always reduce it to the lowest term. So I write square root of 2 equal to a over b in the lowest term. If it's in the lowest term, then a and b must be integers. B cannot be 0, and the greatest common divisor of a and b must be 1. If a fraction is in the lowest term, the greatest common divisor of the top and the bottom must be 1. Now let's continue. Square root of 2 equal to a over b. If I square both sides, I have square root of 2 square equal to a square equal to a over b square. Which means 2 equal to a square over b square. If I square both sides, I get 2 equal to a square over b square. Then, if I multiply both sides by b square, I have 2b square equal to a square. If I multiply both sides by b square, I get 2b square equal to a square. Since a square equal to 2 times b square, that's an integer. B is an integer. So b square is an integer. Since a square equal to 2 times integer, then a square is even. Since a square equal to 2 times the integer, since a square equal to number 2 times the integer, then a square must be even. Remember, even number is always 2 times the integer. If s is even, then s equal to 2 times the integer. So since a square equal to 2 times the integer, a square is even. If a square is even, by a theorem we did earlier today, if s square is even, then s must be even. That's a theorem. That's a proof we did earlier today. If s square is even, then s must be even. Since a square is even, then a is even by a proof we did earlier today. Since a square is even, then a must be even. That's a proof we did earlier today. A is even means what? A is even means a equal to 2n. A is even means a equal to 2n, where n is an integer. A is even means a equal to 2n. If I square both sides, that means a square equal to 4n square. If I square both sides, square left side, square. If I square left side and right side, I get a square equal to 4n square. Then, since 2b square equal to a square, and a square equal to 4n square, then we have, I can plug in here, since 2b square equal to a square, and a square equal to 4n square, then 2b square equal to 4n square. Since 2b squared equal to a squared is 4n squared, so 2b squared equal to 4n squared. 2b squared equal to 4n squared. That means if I divide both sides by 2, b squared equal to 2n squared. If I divide both sides by 2, that means b squared equal to 2n squared. N is an integer. B squared equal to 2 times the integer. If b squared equal to 2 times the integer, that means b squared is even. If b squared equal to 2 times the integer, that means b squared is even. Since b squared is even, by a theorem we did earlier today, since b squared is even, b is also even. Keep this proof in mind. If s squared is even, then s is even. Keep this idea in mind. Since b squared is even, b is even. Then b is even means what? B is even means b equal to 2k, where k is the integer. B is even means b equal to 2k, where k is the integer. Then, since a equal to 2n, b equal to 2k, then 2 is a common factor between a and b. Since a equal to 2n, n is the integer. B equal to 2k, k is the integer. That means 2 is a common factor of a and b. Since a equal to 2n, b equal to 2k, where n and k are integers, then that means number 2 is a common factor or common divisor. It's a common divisor of a and b. If 2 is a common divisor of a and b, then the greatest common divisor of a and b must be greater or equal to 2. Since 2 is a common divisor of a and b, then the greatest common divisor of a and b must be greater than or equal to 2. That's a contradiction of this, because we already reduced a and b to the lowest term. Because we already reduced a and b to the lowest term, so the GCD of a and b must be 1. Here we show that GCD of a and b is greater than or equal to 2. That means GCD of ab is not 1. It's a contradiction. It's a contradiction. This is something impossible. It contradicts with our assumption here. So it's a contradiction. Once we find contradiction, that means the assumption was wrong. Once we find contradiction, that means the assumption was wrong. So square root of 2 cannot be rational. That means square root of 2 cannot be rational. So it must be irrational. Since we find something impossible, that's called contradiction. Once we find contradiction, that means the assumption was wrong. So square root of 2 cannot be rational. It must be irrational. Next example, prove or disprove each of the following statements. Prove or disprove each of the following statements. Now, if a problem asks you to prove or disprove, you first need to decide, is this statement true? If the statement is true, we prove it. If the statement is not true, we try to find an example to show it's not true. The statement says, if 2s plus 7 is odd, then s is odd. If we can find an example, that makes the hypothesis true and the conclusion false. If we can find one example, make the assumption true, make the hypothesis true, but the conclusion false. We know that true implies false is false. Then we can disprove this statement. Otherwise, if the statement is true, we have to prove it. When we prove it, we cannot use examples. When we try to prove a theorem, we cannot use examples. But when we try to disprove a theorem, to show a theorem is not true, to show a statement is not true, we can give an example, show that hypothesis is true, but the conclusion is false. Then true implies false is false. First of all, think of this. Can we find an example? Can we find an example that make this part true and make the conclusion false? If we are able to find an example that make the hypothesis true, conclusion false, then that's enough to disprove this theorem. Otherwise, if we can't find any examples to show this statement is false, then it must be a true statement. We have to try to prove this statement. So here, can we find an example that makes this number odd, this number not odd? Can we find an example make this number odd, this number not odd? Let's try. If I let s equal to 1, what do I get? I get 2x plus 7 equal to 9. That is odd. So I make it true here. What about this part? S is odd. That's also true. 1 is odd. That's also true. True implies true doesn't tell us anything. True implies true doesn't tell us anything. We try to find something true implies false. Let's try a different example. Let s equal to 2. Then what do I get? 2x plus 7 is 11. That's true. That's true. 11 is odd. That's true. How about x? S equal to 2. 2 is odd. That's false. So that's a good example. Shows that hypothesis is true, conclusion is false. So that's an example. We can use this example to disprove this statement. This is a false statement. If we find one example that makes this statement false, then this is a false statement. We can use this as an example to disprove this statement. And this example is called a counterexample. So, first of all, we need to tell this is a false statement. In order to disprove this false statement, we give a counterexample. Let s equal to 2. Then 2x plus 7 equal to 11, which is odd. Let's make hypothesis true. But s equal to 2 is even, it's not odd. Let's make the hypothesis false. True implies false is false. So that's a disproof. That's a disproof of this statement. That shows this statement is not true. So we use proof to show a statement is true. We use disproof to show a statement is false. Usually we use a counterexample to show a statement is false. To show a statement is true, we must prove it. To show a statement is false, we can use a counterexample. One example is enough to fail a statement. Next example. The sum of two irrational numbers is irrational. The sum of two irrational numbers is irrational. Can we find two irrational numbers whose sum is not irrational? It's just true that the sum of any two irrational number is always irrational? Can we find two irrational number whose sum is rational? If we can find one example that makes this statement false, then this is a false statement. Otherwise, this is a true statement. We have to prove it. If we can find one example that makes this statement false, then this is a false statement. One example is enough to fail a statement. To fail a statement. One example is enough to fail a statement. But if it's true, we have to prove it. Can we find one example that makes this false? Let's try this example. We know pi is irrational. Or let me use square root of 2, is easier. We know square root of 2 is irrational. Negative square root of 2 is also irrational. But if I add them up, what do I get? If I add them up, I get 0. They are both irrational. But when I add them up, I get something rational. 0 is rational. 0 can be written as 0 over 1, where the bottom is not 0. That's integer over integer. Bottom is not 0. 0 is rational. The sum of two irrational numbers here is not irrational, it's rational. That means this statement is false. So it's a false statement. That's a counterexample. So this is a false statement. We disprove it using an example. Square root of 2 and negative square root of 2, they are both irrational numbers. And their sum, when I add them up, their sum is 0. 0 is rational. That's one example. If this statement is not true for one example, then the entire statement is false. One example is enough to fail a statement. Next example. The product of a rational number and an irrational number is irrational. The product of a rational number and an irrational number is irrational. Is this always true? When we multiply a rational number and an irrational number, do we always get something irrational? Is this always true? If we can find one example that makes this statement false, then this statement is false. Otherwise, if we cannot find any example, this may be a true statement. We have to prove it. So let's guess, is this true or false first? Try some example first. Rational number times irrational number is irrational. Is this always true? We know 0 is rational. Square root of 2 is irrational. If I multiply 0 times square root of 2, what do we get? We get 0. That's rational. But the problem says the product of a rational number and an irrational number must be irrational. So this example is enough to make this statement false. One example is enough to fail a statement. So this example makes this statement false. So here we know that this is a false statement. To disprove it, we use the example. X is rational, square root of 2 is irrational. Rational times irrational is rational. That's an example. That's a counterexample to this statement. Let's call a counterexample to this statement. This is a counterexample to this statement. Next. if 2s plus 1 is rational, then x is rational. If 2s plus 1 is rational, then x is rational. If 2s plus 1 is rational, then x is rational. This statement, it looks true. We can try we can try to plug in some numbers. It looks like this is always true. We can try many examples. As long as this is a rational number, x must be rational. It looks like a true statement. So let's prove it. Let's try to prove it. This looks like a true statement. Let's prove it. So, since if 2s plus 1 is rational, then 2s plus 1 equal to a over b, where a and b are integers, and the denominator b cannot be 0. Then, in this equation, 2s plus 1 equal to a over b, I try to solve for x. I can first of all subtract both sides by 1. So 2s equal to a over b minus 1. That can be rewritten as a minus b over b. Next, in order to get s by itself, I can multiply both sides by half. Multiply both sides by half. So s equal to a over b over 2b. Since a and b are integers, a minus b must be integer. Since b is an integer, 2 times b is also integer. And since b is not 0, then 2 times b cannot be 0. Since b is not 0, 2b cannot be 0. Since s equal to a minus b over 2b, where the numerator a minus b is integer, the denominator 2b is integer, and the denominator 2b is not 0, then x must be rational. That's a proof. That's a proof to this statement. So in general, let's try some examples. If no matter what example we plug in, this is always true, then this may be a true statement. We'll try to prove it. But if we can find a counter example, if we can find one example that makes the statement false, then we can use it as a counter example to disprove the statement. So if a problem asks you to prove or disprove, we first of all need to test if the statement true or false. If it's true, we prove it. If it's false, we give an example. One example is enough to fail a statement. One example is enough to fail a statement. That's called counter example.